eighth lecture on Schrodinger equation in 1D. Today we shall discuss the quantum mechanics of uniform circular motion. In classical physics, we know that a particle moves along the circumference of a circle with uniform angular speed omega. We want to study the corresponding the same system in quantum mechanics. Before going to the quantum description, let me first discuss classical description of the system. That is, I want to find out the Hamiltonian of the system. The particle, if we use polar coordinate, that is, if the point on the circle has coordinate a theta, where a is the radius of the circle, then r is constant and is equal to a. Then the position of the particle is given by a r cap, and the velocity is governed by the velocity is r dot is equal to a r cap dot. This is equal to a theta dot theta cap. This is the velocity. So the kinetic energy, T is equal to half m v dot v. So it is equal to half m s square theta dot square. The Lagrangian L is equal to T minus B. Since there is no potential energy, it is half m s square theta dot square, and the momentum conjugate to theta is governed by p theta is equal to del L del theta dot, and this is equal to m s square theta dot. This is the momentum conjugate to this, that is angular momentum. The Hamiltonian of the system is H is equal to, this is classical Hamiltonian, is equal to p theta theta dot minus L, and remember that H is a function of theta and p theta, whereas Lagrangian is a function of theta and theta dot. On using this and introduce replacing theta dot by p theta, we get this is p theta square by twice I, where I is equal to m s square is equal to moment of inertia of the particle about the origin. Now if we want to quantize this system, now come to the quantum description. So Hamiltonian is replaced by Hamiltonian operator, and this is 1 by 2i is not a dynamical variable, so p theta operator square, so this is 1 upon 2i. P theta operator is I h cross del theta, which is obtained from the basic commutator relation. Basic commutator relation is q alpha p beta is equal to I h cross delta alpha beta. So all together this becomes minus h line square by twice I del 2 del theta 2. This is the Hamiltonian. Now coming to time independent Schrodinger equation. It is H psi here, the single, it is a one-dimensional problem. So this is again a 1D problem, but not in rectangular coordinates but in polar coordinates, is equal to E theta, E, or minus H line square by twice I. Since it is time independent function, so we use total derivative instead of partial derivative, and this gives you psi double dot, that is double derivative of psi with respect to theta, is plus k square psi is equal to 0, where k square is equal to twice I E upon H line square, and it is a positive quantity. So the solution of it is, we write psi in the form of a e to the power plus minus I k theta. We write this as this, and that is psi plus minus theta is equal to this. First thing, the normalization leads to the value of this a is equal to 1 upon 2 pi e to the power plus minus I k theta. Now if this angle be theta, then this is also 2 pi plus theta. So the requirement is that here the boundary condition for this system is psi of plus minus theta is equal to psi of plus minus 2 pi plus theta, which leads to e to the power plus minus I 2 pi k is equal to 1 is equal to that is to say k is now quantized. K is kn and is equal to n, where n belongs to integer, and if that is n can have 0, plus minus 1, plus minus 2. Either you take these values in this fashion, then you need not to write plus minus, and if you write plus minus, then the values are 1, 2, etc. So since the solution depends on n, we write the solution as psi n plus minus of theta is equal to 1 upon root 2 pi e to the power plus minus I n theta. And the corresponding energies are, since energy is E is equal to twice I k square H line square k square by twice I. This is H line square k square by twice I. This now becomes, since k is quantized, we write it En is equal to H line square n square by 2I. This is the energy quantizations. So the energy values are quantized. And what is the meaning of plus minus sign? In this case, we find that p theta and Hamiltonian commutes, because Hamiltonian in this system is 1 upon 2I p theta square, and so Hamiltonian commutes with p theta. So the eigenfunctions of Hamiltonian So the eigenfunction of Hamiltonian, that is psi n, is also an eigenfunction of p theta. Keeping this in mind, we p theta operating on psi n plus minus theta. This is p theta is minus I h cross del del theta operating on 1 upon root 2 pi e to the power plus minus I n theta. So the result is minus I h cross is there multiplied by plus minus I n, and the rest of the thing is psi n plus minus theta, because we are left with 1 upon root 2 times this, which is there. And this part is plus minus nh cross psi n plus minus theta. So we find that p psi plus is an eigenfunction, so we write psi plus minus n theta is an eigenfunction of p theta with eigenvalue plus minus nh cross. Now, what is the meaning of plus minus nh cross? That means a particle may move in anti-clockwise direction. When it is moving in anti-clockwise direction with angular momentum nh cross, it is driven by this anti-clockwise. And when the particle moves in clockwise direction, then this is given by clockwise rotation. In the case of angular variables, if the sense of rotation is clockwise, then we call it minus, and when it is sense of rotation is anti-clockwise, we consider it to be plus. So the eigenvalues are, it has eigenvalue plus nh cross and the corresponding momentum value is minus h cross. You see, this is nothing but Bohr's theory, the result of Bohr's theory. Bohr's theory predicted that whenever a particle, an electron moves around a circular orbit and around the nucleus, the angular momentum is an integral multiple of h cross. It is the integral multiple of h cross. Only point of caution is that n is equal to 0. In the case of n is equal to 0, the angular momentum of the particle is 0. That is, the particle doesn't have any angular momentum, so it is executing a rectilinear motion. So that's all about the circular quantum mechanics of a particle moving in circular motion, and which reproduces the Bohr's theory that we are habituated with from our school classes.